Hello, everyone. My name is Ghazanfar Ali. I'm from Texas Tech University. Today, I would like to present my paper, Automating CPU Dynamic Thermal Control for High-Performance Computing. So this is my outline, introduction, background, design, evaluation, and conclusion. There are many factors which can cause CPU overheated, including computational activity from a workloads, cooling infrastructure failure, or usage of some economized cooling techniques. They can increase the CPU temperature. Is it okay to just ignore these factors? Actually, many studies shown that slight variances in the operational temperature can significantly impact the lifetime, durability, and performance of a CPU. So that's why it is very important to monitor and control the operating temperature of the CPU. And in this regard, we have designed an automated and continuous CPU thermal monitoring and control methodology to maintain a CPU healthy in a healthy thermal state using automation, Kraken and Redfish frameworks. We have evaluated our methodology using a cluster of 150 Raspberry Pi nodes. And based on our empirical results, we found that 70 Celsius was the best temperature to trigger thermal control. Our study is motivated by two real-world incidents, thermal incidents, and also one general incident. Yeah. So the first one is about impact of the compute-intensive workloads on the CPU. So this graph shows the thermal behavior of a CPU in a node in the Texas Tech High Performance Computing Center. So there was one heavy workload which was causing this CPU overheated very frequently, and unfortunately, this CPU ultimately got malfunctioned, and we believe this, which could have been avoided by maintaining a healthy CPU temperature. This is another incident which was basically happened also in the Texas Tech. So this happened the air, the chilled water stopped working. Our chiller was stopped working, providing the cold water. So in this way, the whole cluster started becoming hot, and especially at the time of the failure, like a chiller failure, CPUs running a compute-intensive workloads can get overheated very quickly. So therefore, a reliable thermal control mechanism can increase ride-through time for fixing the failure or graceful shutdown. Yeah. Another way is there is another phenomenon like usage of economizers. So due to low energy cost, many HPC data centers are employing economizers for the cooling purpose. And ASHRAE 2016 studies shows that economizers can cause a fluctuation in ambient temperature between 18 Celsius to 27 Celsius from the desired ambient operating temperature. So these fluctuations in the temperature can indirectly increase the temperature of a CPU. Therefore, a dynamic CPU thermal control is highly desirable in this cooling scenario. There are some studies which show relationship between CPU temperature and power consumption and mean time to failure. So this study shows power consumption is directly proportional to the CPU die temperature. And then Arrhenius equation, which basically studies impact of temperature on the failure rate of semiconductor. And then this shows like mean time to failure is inversely proportional to the failure rate of the semiconductor. So we use this mechanism, like we use the dynamic voltage frequency scaling mechanism to increase and decrease the performance of the CPU, because we believe like a power consumption is directly proportional to the CPU die temperature. So we use this DVFS, which is basically CPU FEC, like Linux subsystem. And yeah, we use this mechanism for performing CPU frequency scaling. Design overview. So we use the Kraken automation framework, which is a basically distributed state discovery and control engine that can maintain states across a large cluster of computers. And it works in a parent and child manner. And it is designed to provide full life cycle maintenance of HPC cluster. And so there are some key terms. Configuration state. So this is the configuration state data, which describes the desired state of the computer node. So we can, this is the user configurable data. So for example, I can set my CPU frequency. I can set my CPU temperature. Yeah, so that is my desired CPU temperature. And discovered state is this is the actual state, like which we acquired discovered by performing the monitoring in the Kraken framework. A mutation is referred to an action or set of actions which are performed to achieve configuration state if the discovered state is not same as the configuration state. CPU thermal state discovery mechanism. So CPU thermal state discovery mechanism. So basically, like in our case, in our automation case, like we have two kind of states, CPU thermal state and CPU frequency scaling state. And then we also have two kind of mutations. One is a CPU thermal mutations and CPU frequency mutations. Yeah, so this is now in this slide, like we will talk about CPU thermal state discovery mechanism. And we have two mechanisms to perform a CPU thermal state discovery. One is the in-band and other one is the out-of-band CPU thermal state discovery, which we will study here. In-band CPU thermal discovery consists of HPC cluster, and which include a master node and then a set of different computing nodes. On the master node, we have a parent Kraken, and then on each computing node, we have a child Kraken with its with like a host frequency scaling and host thermal discovery modules. So these modules perform thermal and frequency scaling state related actions on node. And yeah, so because this is the in-band, so it accesses CPU temperature via operating system, so which is basically host thermal discovery module, and then CPU temperature is reported to the parent Kraken node via child Kraken using the Kraken API. And then in-band CPU thermal state discovery. So more information about in-band CPU thermal state discovery. So we, like CPU temperature, which we acquired from the CPU sensor, is just a number. So we have to provide a characterization into CPU temp normal, CPU temp high, CPU temp critical using the predefined thresholds. And then overall procedure for the in-band thermal state discovery includes 3 key steps. As a first step, host thermal discovery will read the CPU temperature sensor. And then after getting this data, this number, it will be characterized into one of this state as a step, after performing this this categorization. then this thermal discovery will be reported to the child Kraken, and then child Kraken will synchronize this state to the parent Kraken node. And then the next one, we will study about the out-of-band CPU thermal state discovery. So for the out-of-band, like we are using Redfish API, which is defined by the DMTF Redfish group. This is DMTF is a basically distributed management task force, and it is Redfish is basically a standard that is widely adopted in many HPC server products, and it exposes an interface to access baseboard management controller through Redfish API. So overall procedure or the deployment mechanism look like this. Like we have again like a master node will host a parent Kraken, and parent Kraken will have a RF thermal discovery, that is Redfish thermal discovery, which communicate to the Redfish aggregator, and then which talk to Redfish aggregator, basically talk to the HPC cluster, different nodes in the HPC clusters using Redfish API, like basically to the BMC of each node using the Redfish API. So this is the Redfish aggregator is basically a single entry point for the parent Kraken. So it's so what will happen is like a Redfish thermal discovery want to read the CPU temperature of each node. So what it will do like it will initiate a Redfish group request, it will be a single request for the whole cluster to the RF aggregator. Then RF aggregator will fans out this Redfish request to each node, and then each node will report the CPU temperature via BMC to the RF aggregator. Then RF aggregator will combine all the responses into one single response and send to the RF thermal discovery. So this is how we perform out-of-band thermal state discovery. So what are the benefits of doing it? So we can see right now there is no child Kraken, and there is no need for any like on-node Kraken module. So it is very clean and it is agentless. Second thing, because we are using BMC capability to acquire the CPU temperature, so it has also like a node's temperature will be not used in executing any Kraken module or any child Kraken. So that's a very clean and very efficient way to access the CPU temperature. And this in-band or out-of-band, this is completely, we can use one of the approach. It depends upon the choice of the data center operator. CPU frequency scaling is this is the second mechanism for this automation. So this involves so because the frequency scaling is not supported by any BMC technology, so that's why it must have to be in-band. It has to use the in-band mechanism, and it has to be done on node using the operating system. So it includes 3 steps. As a first step, Kraken child will check the frequency scaling mutation, and then it analyzes whether it has to change the frequency or not. If it determines like it has to change the CPU frequency, then it will talk to host frequency scaling set, and then host frequency scaling set will set the desired frequency of the CPU. And then for the monitoring purpose, like CPU frequency will be, Kraken will also monitor the current CPU frequency using step A and B, and then all these 2 things, like all these mutations and also the frequency scaling state will be synchronized with the parent node. So that's, and then like there are some state diagrams of the CPU thermal mutations and CPU frequency scaling mutations. So as a first step, this CPU thermal state mutations allows Kraken to control CPU thermal state. And these are the possible mutations, like if the temperature is if CPU temperature is if the CPU temperature is high, it can mutate from high to normal, and if the CPU temperature is normal, due to some external factor like CPU temperature can go into CPU temperature high, and it can also go into the CPU temperature critical. And the similar way, like if the CPU temperature is critical, it can be healed, it can be reduced to CPU temperature normal. And then we have a CPU frequency scaling mutations. Mostly it is like it switches back and forth between power save, and then if it is in performance mode, it can be switched back to the power save, and if it is power save, it can go into the performance. And the CPU frequency scaling mutations are governed by real-time CPU thermal states. So it has some dependency on the CPU thermal mutation. For example, if CPU temp is high and the frequency is in the performance mode, then Kraken can perform a mutation from performance mode to power save mode. And as we can see from in our previous slide, like it's power save to performance and performance to power save. And then, and whenever CPU, like a Kraken discover like a CPU is healed or it is back to the CPU temperature normal, and CPU frequency is still in power save mode, then it will initiate a new mutation or action, which will from power save to performance. So in this way, because there is no reason when the CPU temperature is in normal base, so it can be switched back to performance mode. Implementation, our implementation hardware setup include like 150 Raspberry Pi nodes and one master node and an external fan. And software stack includes, and then these are the couple of Kraken modules which are required for our implementation, which we have done with this 150 Raspberry Pi nodes. And then this is a Kraken dashboard. Like this is a Kraken is an like as we know, like it's a automation and control framework. So this is developed by the Los Alamos National Laboratory, and this is an open source framework. And yeah, so this is like every we can this node can be, we can put different kind of we can assign legends. So the thermal state legend is represented by the border. So this this particular node is in the border is in yellow. That means it's an overheated CPU. Maybe as a CPU temperature is high, it's not in critical. If it is, and then this is CPU with a normal temperature. So this, if its border is in green, so that means that CPU is with a normal temp. And so, and then we have performed some other evaluation. The first one is we want to see the CPU temperature behavior, CPU thermal behavior, and also CPU frequency behavior. Without applying any control. So this like right y-axis is showing the CPU frequency, which are basically two, like lowest and highest, and the left y-axis is showing CPU temperature behavior in Celsius, and x-axis is showing time in minutes. So this is the behavior of the CPU with the lowest frequency. So we can see it is approximately around 70 Celsius without applying any control. And because like we are cooling this CPU, the whole cluster using external fan at room temperature. So that's why it attained the high temperature at 20 minutes, and then it continued with the same temperature. And then the next one is we also studied the CPU thermal behavior with the highest frequency in the performance mode, which is at 1200 megahertz. And we saw like in almost half of the time, it reaches in approximately in 10 minutes to the highest temperature, which is very dangerous. Like it's almost thermal, it's almost near to the CPU thermal shutdown. So it's 10 minutes, like, and then it continued with the same temperature because we are again cooling it like with we have a external fan to cool the cluster. And then our next 4 slides are basically we have studied the impact of different CPU temperature thresholds on CPU temperature and the frequency. And so here, like we apply CPU thermal control at 50 Celsius. What does it mean? It means CPU, whenever CPU temperature reaches to 50 Celsius, so we are clocking the CPU to the lowest frequency. So there are some kind of a back and forth between highest and the lowest frequency. And then regardless of the, and then it went to the like lowest temperature because the temperature was like, it's still like continued. And then within 20 minutes, like it reaches to its maximum level, which is kind of like less than 70 Celsius because we are heated. We are still like cooling through the fan. So it like then it went to the, it has never crossed the 70 Celsius for like we tried within for half an hour at least. And then we tried the same experiment at 50 Celsius. So we got almost similar behavior. And then we tried the similar experiment with the 60 Celsius. So this time there is a more back and forth between highest frequency and the lowest frequency, but other parameters are the same. Like it is not, it's approximately the maximum temperature increase was around 70 Celsius. And then we also did the same experiment with the 65 Celsius, similar result. And then we did with the 70 Celsius. And then we saw a lot of back and forth between CPU, between the CPU highest and lowest frequencies. And so basically what is happening whenever temperature crosses 70 Celsius, then our thermal control system will clock the CPU at the lowest frequency, which is 600. And then whenever the temperature is healed less and it becomes less than 70, then it is clocked back to the highest frequency again. And then like whenever it's in highest frequency, then temperature will again increase and then the same cycle will go on. And then like with the 75 Celsius, even we are seeing this back and forth more consistent, and actually it will continue for like even for like it went for a long time, even for the remaining whole half an hour. So that is very dangerous for the CPU life cycle itself. So this back and forth is not good. Like there are a lot of overheads on the CPU in terms of like context switching. So maybe this like just a threshold based scale like is scaling is not a good, control is not a good idea. So and then like we also did on the 80 Celsius, so which is basically showing CPU there is a kind of like an initial some kind of like between lowest frequency and highest frequency, and then at the end even it put the frequencies on the lowest mode, but still temperature is rising because our intervention is 80 Celsius, so it is around 85. So it continued because still we are cooling like a CPU using the fan. And this is experiment with the 85 Celsius. And here we see there is some, most of the time like a CPU is on highest frequency, and there are very few times like the CPU is going back to the lowest frequency. That means there is a very less control over here, and there's it's very there is almost no control on in cooling down the CPU. So discussion and key takeaways. So we studied the impact of applying thermal control at 8 different temperature configurations. Applying thermal control at the lower temperature configuration restricted temperature at to 70 Celsius. Applying thermal control at upper temperature configuration resulted in attaining higher temperature, close to 85 Celsius. And then there is a quite back and forth switching between performance and power save modes for some temperature configurations. So that's why, so there are two key takeaways. One is applying thermal control at the lower temperature configuration is better to slow down the overall temperature progression. Like maybe 70 is the ideal in our experiments. And then applying thermal control for a certain interval is more desirable than just a temperature threshold based thermal control to avoid this back and forth. So setting, like for example, we can just let the cool down CPU for half an hour, and then it will be more stable, and then we can put the temperature CPU frequency back to its performance mode. Otherwise, there can be a lot of back and forth, which is not desirable. Modern CPUs are prone to overheating in unfavorable thermal conditions. And we have successfully, our experiments have shown us like automated healing can be, like we can heal an overheated CPU temperature in an automated fashion. And our method also allows scaling up the CPU frequency when the CPU thermal state is back to the normal. And implementation leverages state-of-the-art Redfish and Kraken, which is an HPC automation and control framework. And we are also interested to continue the study, especially we want to study about how to coherently heal a node involved in a group of nodes, for example, for MPI jobs or workloads. And we also want to add some design pattern for the graceful shutdown of a node when the CPU thermal state reaches an irreversible critical level. Thank you very much for your time. And for more details, please read our paper. Bye. Please let me know if you have any further question or any. Yeah, thank you.